So, hi everybody, welcome to our today's seminar. So today's speaker is Renan Assimos from recently University of Hannover, before Max Planck Institute in Leipzig, and he will talk about the spherical Bernstein theorem by Solomon.
So hi everybody. First of all, thanks for the organizers, for the invitation. So everything I will present today is in a joint work with Jost, which was my PhD advisor in Leipzig. And okay, so today I will talk about spherical Bernstein theorems. And I will, so this result of Solomon is essentially going to be like, so an application of some techniques that I will present. And then as I wrote, like in the abstract, so usually I'm concerned with problems in higher codimension. And I will try to see if we can arrive there today to higher codimension, but I only promise codimension 1 results today. Okay, so I would like to start with a historical introduction. And this historical introduction is going to be a little bit long, but it's just so that we can introduce spherical Bernstein problems. And the thing is, so first of all, the first question for those who are not familiar, so what is Bernstein problem? So what is Bernstein theorem? So everything started in 1915 when Bernstein proved the following theorem for minimal surfaces. So he considers a function f from the entire of R2 to R. So this function is smooth, and so in this talk, every manifold and function is going to be taken smooth. So, and then he looks at the graph of such a function and considers this graph, and he supposes that this graph is a minimal surface in R3. Then the conclusion is that the sigma must be a plane. So there is no minimal surface that is the graph of a function given by the graph of a function except the trivial one, which is the plane. So a totally geodesic thing. And just to familiarize ourselves, so there are many generalizations of this theorem, also some counterexamples, whatever. And so I'm just going to give a brief overview of what is this. So, so there were many things, many works by Di Giorgi and Almgren and people doing GMT and things like this to generalize Bernstein theorems for higher dimensions. I will skip those and I will talk directly about a result by James Simons in 1967. And Simons essentially proved the following. So if you take P to be between 2 and 7, and you suppose that you take a function from Rp to R, a smooth function. So if you suppose that the graph of such a function is a minimal hypersurface of Rp plus 1, then sigma is a plane, is a p-plane in Rp plus 1. So again, P at most 7 in my notation. So, okay, this is like Simon's result. And so here I comment that, so there were, so Di Giorgi has proven this when P was 3, Almgren was P was 4. But the interesting fact is that if P is bigger or equal to 8, right after Simon's result, Bonghieri, Di Giorgi, Giusti, they have obtained a counterexample for a full Bernstein theorem from functions from R8. So essentially they prove that the Simons cone is a Lipschitz solution to the minimal surface equation, but its graph, it's not hyperplane in R9. So I put this just to, this is not going to be important for us. I just put this to, so that we know that this problem has some very difficulties when we are looking at higher dimensions and especially in higher codimensions. Okay, so, but still in the case of the classical case of Bernstein, there was a result by Moser, which is actually from 1961, so before the result of Simons, that is a positive result of Bernstein type But it has an additional assumption. So essentially, he says, well, you take a function now, f, defined on Rp for any p, taking values in R, and you suppose that the graph of this function is a minimum hypersurface in Rp plus 1. Okay? And in addition, he supposes that the gradient of this function is uniformly bound. So the vector norm of the gradient is bounded by a number. Here I denote by beta 0. So he concludes that then this function is indeed linear and its graph is just a p-plane in Rp plus 1. So under the additional assumption of the bound on the gradient, he gets some still a Bernstein problem. So somehow, because of the counterexample of Di Giorgi and Bombieri and Giusti, and this result of Moser, we know that perhaps now we are looking for some sort of like calibrating some hypothesis to see whether we can get still some rigidity a la Bernstein for the problem when we increase dimension. So this is what is so-called the classical Bernstein theorem. And now so Shen has introduced in his address to the International Congress of Mathematicians a problem that he called the spherical Bernstein problem. And he called it an outstanding problem in differential geometry. And it reads like this. So now we are going to change. So now we are going to consider hypersurface not anymore in the Euclidean space, but in another very famous space with a constant curvature, which is Sn. So then he says, well, consider an embedded minimal sphere of codimension 1 in Sn. Is it necessarily an equator, or in other words, is it totally geodesic? So is it like a plane in Rp plus 1? So this is the so-called spherical Bernstein problem, okay? And just a remark that the beginning case, so when n was equal to 3, was already known by Almgren. And here I put the reference. Okay, so this problem is, let's say, somehow more difficult than, or more subtle than the classical Bernstein theorem, because he's young, he has constructed infinitely many distinct new examples of minimal embeddings of Sn minus 1 into Sn when n equal to 4, 5, 6. So therefore, even in dimension 4, such a spherical Bernstein problem do not hold, okay? All right, so this results of Hsiang. And now we will try some sort of like a Moser approach. Can we actually add some extra condition on this spherical Bernstein problem so that we can still guarantee that this is going to be totally geodesic? And the condition I'm going to try to motivate ourselves is, okay, so what if we added the condition that the normal planes, so the normal planes of this hypersurface, if they do not change much their direction, and much we will try to define very soon, or if we want to rephrase this, we want to impose some condition on the Gauss map of such a minimal hypersurface of Sn. Okay. So what if we restrict the set where the image of the Gauss map can be? Could we then get some rigidity result a la Bernstein, I meant. So for instance, let me say why we are talking about the Gauss map. So the Gauss map of a graph, of an entire graph from a function from Rp to R, is contained, so the Gauss map is contained on the closed upper hemisphere of a sphere, right? And if you look at what the extra condition on Moser's result, which is that we add that the gradient of this function is bounded, then we can actually prove that the image of the Gauss map is contained in an open hemisphere. Okay, and here that's going to be an important thing for the talk. So obviously the open hemisphere of a sphere is a convex set. Okay. All right. So and one thing is like, so let me now try to explain why it's nice to look at the Gauss map. So so Bernstein theorem, we want to prove that under some extra assumption, we have that a minimal surface will be a plane, right? Either it's a graph or a graph of bounded slope or whatever condition we put on it to restrict the Gauss map. So if I look at the Gauss map, at the normal Gauss map of some hypersurface, so these Gauss maps, like, so here's like the tangent space at the point of my surface. So if my surface is a plane, this means that my Gauss map is constant. It doesn't vary. So somehow obtaining a Bernstein, so proving a Bernstein theorem is proving that the Gauss map of your hypersurface is constant. Okay. And then here it will enter something which is, so I will not write this down, I just put it as a remark. It's that the Gauss map of a minimal submanifold is a harmonic map. Okay, so this Gauss map for us is always going to be harmonic because it's always taken on a minimal submanifold. So then what we are going to try today is to prove that a harmonic map, namely the Gauss map, is constant. And this is going to tell you that we are in a flat, in a totally geodesic space. This is true for the classical Bernstein and also for the spherical Bernstein. So the definition of the Gauss map changes a little bit, but it's essentially the same. Okay, so one comment is that there is a theorem by Jost, Shin, and Yang, and this is a result of the JDG 2012, if I'm not wrong, that they say that, okay, here for Moses' result, we assume that if our Gauss image is contained in an open hemisphere, then our Gauss map is constant, okay? And this is essentially because here, this is a convex set, so it admits a strictly convex function, and then we can use like some maximal principle to get that the Gauss map is going to be constant if it takes values in such a set. But indeed, Jost and Yang, they said, okay, the Gauss map would be constant. Sorry, here I made a mistake. There is no compactness here. I stated wrong. I'm sorry. So they said, okay, if the Gauss map of a graph is contained in Sn, removing this set, which I'm going to explain what it is, then this Gauss map is constant. This set here, so this is a totally geodesic codimension 1 subsphere, and this is a quotient by the antipodal map. So imagine this in S2 is like if I take, so perhaps I'm going to draw. So this is like if I take like half of an equatorial sphere, and now I have to, so I will try to share my screen here with the other gadget that I have. So just a second, let me share my screen here. Sorry, I'm having a slight problem. How can I share content, share screen? It's not working. Perhaps I have to stop sharing here. Does that work? Okay. Well, that's not working.
How about I share a whiteboard? I think then you can draw on it.
That could help. Sorry for this. I thought it would have worked.
So now I share a whiteboard, I hope.
Okay. So this set that I'm talking about is, I would draw it, of course, only in dimension 2, but the idea is the following. So imagine, so I have a sphere, okay? So this is S2, or we can say Sn. Well, let's say S2. And imagine that here I pick two antipodal points, okay? And I connect these two antipodal points by a geodesic, so half of an equatorial subsphere, and I take a like open subset of these sets. So then I say here's S2, and I remove half of an equatorial S2. Okay, so then Jost and Yang, they proved that in the complement of this set that they removed here, in the complement of this, there exists a strictly convex function. So there exists a strictly convex function on every k that's compactly supported on this set. Okay, and with the help of this function, they managed to get some maximum principles, so that if a Gauss map of some graph is contained in the complement of this region, then it must be constant. And so this set is going to be very important for us, and it's going to be an example of, it's going to be an application of what we are doing today. And I will go back to this. I'll go back to this. So essentially, so you don't need to be your Gauss map to be only on the north hemisphere, but you could actually have it be in a much wider set. Okay, so let me reshare my screen here. Thanks. All right, so this is the result. I stated slightly wrong. So we present a proof for this today. All right. And now, okay, so we deviate a little bit talking about some classical Bernsteins, but now going back to the spherical Bernstein problems. Despite the negative results of Hesse-Young, there is a very nice and positive result of Solomon, which we'll try to present a proof today. And he gets the following positive result also in arbitrary codimension. So he showed that for the spherical case, the Gauss map actually can omit a much bigger set than the one of of Jost, Shin, Yang before, with an addition, so in the spherical case and with an additional hypothesis. So Solomon proved the following theorem, and so this is a theorem from 84, so like 1 year after Hesse-Young's results. So if you take M to be a compact minimum hypersurface of a sphere as n plus 1, and you suppose that H1 of M equal to 0, so this is the extra hypothesis he's going to put. This is the first Dehaene cohomology group for us. And he also assumed that, suppose that the Gauss map omits a codimension 2 equatorial subsphere, which I denote by Sn minus 1 in Sn plus 1. Then M is an equator. So Armin, can I ask you to share again the white board with me? Sorry, Armin. Oh, thanks.
Here it is.
I just want again to draw, or maybe we can we clear all this? Okay. So here a small picture of what I draw before, right? So there was this half equator thing, right? And now what is in the result of Solomon, what is the set that he actually omits? So in this two-dimensional picture, he actually omits only these two. He omits an S0, right? So actually a neighborhood of an S0 in here. So then he says, okay, if the Gauss map of the submanifold of this hypersurface of a sphere, minimum hypersurface of the sphere, omits the neighborhood of an equatorial codimension 2 sphere, then this Gauss map must be constant, and therefore we get the Bernstein result. So therefore this must be a totally geodesic subspace of Sn. But of course he phrases this as and as we're gonna do Sn without Sn minus 2 equatorially embedded. So this is a subsphere. Okay. So all right, I go back here sharing my screen. And this is going to be the result that we are going to present a proof today. Okay, but to present a proof for such a thing, I want to then talk about something that I have been developing with Jürgen Jost in the past couple of years, and it's about some applications of the maximum principle. Okay, so I will talk about.
Sorry, can I ask you a quick question?
Sure.
On the title of Solomon's paper says that it applies to area minimizing surfaces.
Yes, but because he also gets another type of Bernstein result there. This is
okay.
So there are two types of results that I'm just presenting one.
Okay.
So
thank you.
So I think you are talking. So I am talking about theorem 1 in his paper, and probably the area minimizing one is the theorem 5. But,
all right, gotcha.
Yeah,
Thank
it's
you.
another one. Okay, so regarding maximum principles, I will talk about a maximum principle by Samson, and so here is the statement of the maximum principle. But I would like to ask Armin to share the screen with me again, please.
Sure, just a second.
It will happen sometime. Sorry. So,
should I erase?
Yeah, if you can, please. All right. So the Samson maximum principle, which I'm gonna denote here just as an abbreviation as SMP, Samson maximum principle, says the following. Okay. We'll first suppose we have a compact manifold. So M is compact and has no boundary. So also I forgot to say that, but no manifold here has boundary for us. And we consider a harmonic map phi non-trivial, okay? And our target manifold is only a complete, so it's complete manifold, okay? And then he says the following. Well, suppose you take a point X here on your domain, and you look at the image of X, so phi of X, via your harmonic map, and you suppose that in here there exists S, which is a hypersurface, and this hypersurface enjoys some convexity. So it's a convex hypersurface, meaning that the second fundamental form of phi points to a given direction, so it's definite. So this part here, I'm gonna use it later. This is called the concave side of S, okay? And then Samson maximum principle says the following. So if there exists such a hypersurface, for every neighborhood here, U of X, there will exist a point that we can call X prime, such that the image of this point belongs to the convex side of your hypersurface, so to this side here of your convex hypersurface. Or in other words, he says that if you look at this neighborhood here, this neighborhood cannot be mapped entirely on this part. So this thing cannot happen. Okay, so you must find a point on the other side of your convex hypersurface S. Okay, and then this is Samson maximum principle, and then I will talk about now this a result that we got by me and Jürgen. So Armin, could you erase again this? So I will later show the statement on the slides. I just want to explain. So then, so that is Samson maximum principle. And now, so there is this result, which is by me and Professor Jost. It was in 2018. And what we do is we iterate this maximum principle by Samson. So we suppose here the following. So suppose that we take a manifold N complete, okay? And we look at a ball. So this set here is a ball, like so. This ball has some radius r, and the important thing is that this radius is smaller than the convexity radius of M. Okay, and I'm gonna call this point here gamma of A, and it's gonna be clear why I'm calling this. So I take a ball centered in this point gamma of A with radius r, and then I suppose that there exists some smooth curve here in my manifold, gamma B, okay? Sorry, the curve gamma, the final point is gamma B, and in each point of gamma of the curve, I will consider the ball. So I will construct a region more or less like this. So this last set here is B gamma B R. And if we call this region R, so this region is essentially by definition is the union of all these balls, gamma B R. So we will put some conditions in such a region that is given by the union of such a family of balls, so that we cannot find harmonic maps in a region like this. Okay, and the condition we are going to put, I will write here right now, is the following. So we suppose that R is such that so we suppose that R satisfies that for every t which belongs to the interval AB open, we have that R without the ball at gamma T0 R is disjoint. So I write this precisely on the slides, but what I'm just saying is that if you pick any T0 which is bigger than A, smaller than B, which is going to be here. So if you remove this ball, you divide your set in two parts, right? So it's going to be a disjoint set. So it's going to be this and this, okay? So I say, okay, what is this condition about? Well, this condition is about somehow I don't want my curve to do some weird things like have self-intersection or be very close to each other like this and take very big balls. So my curve becomes something very weird. So I don't want these things to happen. And the conclusion is that if R is a region on a manifold that is complete and satisfies such a condition, then there exists no harmonic map from a compact manifold without boundary into N, H, whose image is contained in R. So let me write like whose image of M is contained in R, right? So, so what is this theorem about? So, okay, essentially, as I said, this is just an application of Samson maximum principle, and we can even, like, let's say I could draw a proof or a sketch of the proof of this theorem just by right here. So suppose that we take a map from a manifold M, compact without boundary, that is harmonic. So here is phi, and this is harmonic, non-constant, of course. And then we suppose that this map takes values inside this region R. Okay, so then there exists a point here, x1, and this point, okay, and this point x1 is mapped here somewhere. Okay, so this is phi of x1. Okay. So by the construction of my region, what do I have? So since my region is given by the union of balls that are all convex, I managed to find some time, let's call it T1. So there will be a point here like T1, such that the ball of radius R centered in T1. Oh, I'm sorry, the drawing is very bad. Let me undo this drawing. Okay, that was a bit better. So if I find so there will be a point T1 here, such that my ball, it's going to touch phi of x1 exactly in the boundary. So I'm sorry, I don't know why, but my ball is not staying inside of the region, but this ball, this blue ball is B gamma T1 R. Okay. So essentially then I have this point here, x1, in the boundary of this ball. So by Samson maximum principle, there exists a point here called x2, and this point is mapped into this side of my region by my map phi. Okay, and then again I can find another ball that will be contained here. So the idea is that, so okay, since this drawing is going down for some unknown reason, I will share here my screen because I have a better picture of this. Can I reshare my screen? No. Share screen. So okay, what I'm trying to draw, and it's being complicated in tablet, is the following picture. So this is the statement of the theorem. We'll go back to it. Okay, here is better. So since my region is given by the union of convex balls along the curve gamma t.
Renan, I think,
yeah.
Can you go into presentation mode? I think I see only the upper part.
I am in presentation mode.
Oh, maybe it's just me then. Never mind.
No, but actually, I also only see the upper part in my tablet. Perhaps I have to. Well, in my laptop, I am in presentation mode. I don't know what is happening. Let me try to exit and do it again. Do you see it better now?
Same.
Same. Oh, God. I'm sorry. I don't know. Let me reshare the screen once more.
Yep. Looks like
okay, good. Oh, okay, so then the result is essentially the following. So, okay, now I kind of explained there. So since my region is foliated by a union of balls, whenever I find the point of my harmonic map, I can also always find a point, let's say here in the picture, to the right side of my original ball. And then I keep applying this argument iteratively until I show that the image, via using some compactness argument, that the image of my harmonic map leaves this region at some point. Okay, and then we get this result here. So if you take R being the union of balls, then we get that there exists no harmonic map from a compact manifold without boundary that will take values only on this region R. Okay, so it's essentially like iterating some sort of maximum principle many times, we get this result. So here's the picture, and I want to show a couple of applications of this result. So the first application is the following. So suppose that we take, so let's go back to this example here. So which was this that I draw in the beginning. Now, of course, I draw again only in dimension 2. So this thing that appears in the paper of Jost Yang. So we take a ball, S2, and we remove again this neighborhood of half an equator. Okay, and we are going to prove that. So this is a different proof than the one of Jost. So Jost, they proved there exists a strictly convex function in here. We are going to prove that in this set there exists no harmonic map just via constructing a region of balls that can foliate this region here. And how do we do that? So we essentially do in a very easy way. So we are going to take balls that will have radius pi over 2 minus a tiny epsilon, so that this ball is convex because, right, these are balls in a sphere. And we take gamma to be a curve connecting these, so connecting minus 1, 0, 0, the North Pole, and 1, 0, 0. So what I mean is like gamma is going to be a curve coming from here, going all the way up, and then going to here again, okay? So if we define R to be exactly this family of balls, you can see that we are going to take balls that they enter this gray region here, but they don't touch the black line. And then I take the union over everybody. And then I have that my region R contains this S2 minus an epsilon neighborhood of the half equator. And just by using this foliation, without constructing any strictly convex function, we actually get that in this region, you cannot get a harmonic map from a convex, from a compact manifold. Okay, so all right. So the interesting thing of this approach is that we actually can do this approach for things that are much more flexible than this half equator. So let me give an example here. So let us consider a curve gamma that it has only one hypothesis. It's a connected curve connecting two antipodal points. So these points 0, 1, 0, 0, minus 1, 0 are two antipodal points in S2, and we take gamma to be a curve connecting these 2 points. Okay, we can prove that on a neighborhood of S2 minus this curve gamma, there exists no image of harmonic map, essentially doing the same argument that I did before. So, I mean, could you please share again the screen with me?
Yep, just a sec.
Yes.
And I erase.
Can erase, yes. So what I'm now saying is that I am taking a ball, okay, and instead I'm still taking two antipodal points in this ball, but instead of connecting this ball with a straight, so with a geodesic, I am essentially taking and connecting this ball with like a perhaps wiggling line and looking at the complement of this. Okay, so it's not trivial that you can define a strictly convex function on the complement of this, but with our family of balls that we did before, not exactly that family, but with a similar argument, essentially by iterating some so many times via using balls centered in a curve gamma t with this radius, we can actually sweep out this region with convex leaves. So we still prove that in the complement of gamma, there exists no harmonic map. So that's a much more flexible argument rather than finding strictly convex functions. And we need to keep this in mind because that's going to be important for Solomon's result that we want to present. Okay, so essentially here, and just a small remarks that, okay, the analogous of these results, so now I have to reshare, sorry, I have to reshare my screen. So the, oh, again, right, you're not seeing well. Okay, so a remark here is that the analogous of this result, S2 minus gamma in higher dimension, is a bit more delicate, and it appears in the same preprint that I wrote this about this theorem of Solomon. So we also remove something less rigid than totally geodesic hypersurface as n-1. So we also take something that's what is the equivalent of this wiggling set for S2, and we did this in higher dimension. Okay, so now, okay, since time might be running out, I will just pass very fast through this corollary. So this corollary is just that, so R doesn't really need to be given by the union of balls. That's like the spirit of the corollary, is that it's enough for R to be swept out, to admit a sweep out by convex hypersurfaces. Okay, so, and then you need this sweep out to satisfy conditions that are equivalent to the ones we put in the theorem. That so somehow, like whenever you remove a leaf of this sweep out, then R is going to be this disjoint union of connected sets, And you also need like one leaf to be living on the concave side of the other, otherwise, so they cannot cross or they cannot intersect. So let's take this corollary just as a spirit that being a family of balls is not the point here. But being a family of balls helps when we are in symmetric spaces, for example, or spaces where convex balls are very big. Okay, so that's just a corollary to keep your attention that the important things are the foliations. And yeah, so then you can just get the same conclusion. And okay, I am gonna skip this slide, but this slide is a little bit about what happens if you take unions of such regions, and then you have to control foliation in a much more delicate way. It's not always true, and then I will skip it because I think I'm kind of running out of time. And I wanted to talk now about Solomon's theorem. So once again, let me restate Solomon's theorem. So we are looking now at a k-dimensional compact minimal hypersurface of the sphere Sk plus 1, okay? And we assume that h1 of m equals 0, and the Gauss image of m is contained on a thickening of a great codimension 2 sphere Sk minus 1. Okay, so in other words, I wrote it like this, so Sk plus 1, and this is a great Sk minus 1, and this epsilon here denotes that is an epsilon thickening of this totally geodesic codimension 2 sphere. And then if our Gauss map is contained in this region, then we can actually prove that this Gauss map, that this M is going to be totally geodesic hypersurface in Sk plus 1. Okay, so, all right. So, and again, this proof is going to be essentially a corollary not only of Samson maximal principle, but also of the pictures that I draw before. And the idea here is the following. So, first of all, we have M is minimal and its Gauss map is a harmonic map, as I commented before, from M into Sk plus 1. Okay. Okay, but before, so Armin, could you please share your screen once more?
Sure.
And also, can you raise? So, okay. So now, what we want to do is the following. So, we are looking at the set, which is Sn, okay? And we are taking out of this set an epsilon thickening of a codimension 2 subsphere, which here I will denote by S0 because I can only draw in this dimension. And then we are taking a harmonic map, right? That is from a compact hypersurface. So this map is harmonic, okay? Here, this map, sorry, I denoted by, this is the Gauss map, so we denoted by gamma, okay? And essentially, Solomon says that if you look at the image of, so if the image of this Gauss map is contained on the complement, on this region here, then this map is constant. So let's have a look at this proof. So the first thing is that, of course, this region, if you look with attention, you cannot obtain a convex function here, or you cannot obtain really a foliation here, because there are harmonic maps in this region. For instance, there are like, you know, this goes geodesic here on the set, right? And then here it conveys that we can look at the universal cover of such a set. So if we look at the universal cover of this set here, so this universal cover looks like a stripe. In this case here, what we are drawing, like, so it's an infinite stripe, okay, in R2. So this set here that I'm drawing is S2 minus S0 universal cover of this set, okay? And the question is the following. So if we are able to lift this map as a harmonic map, then what can we do? So first of all, here I will consider in the universal cover, we will take like the pullback metric. So I take the pullback of the round metric down here, denote this by psi, okay? And then we have the following thing. So if I manage, so the thing is, if I look at the foliation that I have drawn before, so before I have said that you define a region R as the union of balls centered in some curve gamma t, right? Centered in some curve gamma t with radius pi over 2 minus some epsilon. But now my curve gamma, I just take it as this closed geodesic that I define here. So that's a curve, that's our curve gamma, okay? So now this is like this region can, it clearly cover everything, but it self-intersects and everything. So if I draw only the boundaries of those regions, look at how they would look like. They are some sort of like they foliate this set like this, okay? So this region gives me a foliation of this set. And if I lift this foliation of convex leaf, since this is an isometry, this foliation here essentially looks like this, right? So I will draw, it is foliating this whole family. So if I manage to lift gamma as a harmonic map to the universal cover, here there will appear the image of the compact manifold on a region that's foliated by strictly convex sets, okay? So therefore, this would be constant. And then my Gauss map would be constant in the universal cover. So then it will also be constant down there. So here I will go back to share my screen. So now again, so didn't work. Sorry, let me. Okay. So now the question is, if we manage to lift this map, we are done and we prove Solomon's theorem. So here, okay, as I said, that we are going to consider the universal cover. And then we have the following property. So clearly the pi1 of the set I draw, like S2 minus S0 is Z, right? And we remember that the Hahn cohomology group in this case can be seen as the set of homomorphisms from pi1 of M into Z, right? But by assumption, H1 of M is 0. So the map induced by our Gauss map between fundamental groups is, so gamma induces a map from pi1 into Z. And this is going to be a homomorphism. And this must be then 0, since we have this hypothesis that H1 of M equals 0. Therefore, the lifting exists and it lifts as a harmonic map. So then we can lift gamma as a harmonic map from M, which is compact, into this region. And as I draw in the picture here before, this region admits a strictly convex foliation. Therefore, so admits a sweep out by convex hypersurface. Therefore, we get that, so the theorem follows, right? So it's a harmonic map from a compact manifold into a region that admits a strictly convex foliation. So this map must be constant, and therefore the Gauss map is constant. Therefore, M is totally geodesic in SK plus 1. And now I use my last 30 seconds to talk about how this approach allows us to generalize to higher codimension. So Armin, can I get the slide for the last time, the screen? Can also, okay. So the thing is, like, now if we want to have such an approach to higher codimension, now we have a problem that the target manifold is a Grassmannian, but I will draw as a sphere. And the idea that we use to generalize this result is that we still ask this hypothesis H1 M is equal to 0, so that we manage to lift the map to the universal cover. And then what we look for is like, so this guy now here denotes the Grassmannian, let's say GPN plus. And what we look for is a convex ball in the Grassmannian. Okay, so this ball have some radius. And then we also look at a direction where we can rotate this ball like we did, so that we cover a very big region on the Grassmannian. So this is exactly what we did for Solomon, right? So, but for Solomon's, this ball, we all know it very well. So it's just an open hemisphere. And the set that if you rotate the open hemisphere, the set that it excludes is a codimension 2 subsphere. And for the Grassmannian, this is is more complicated. And then you also have to take care with the dimensions here of the Grassmannian, because I mean, for example, if you take a Grassmannian, let's say oriented Grassmannian 4 in the space 200, so maybe the set that you omit has codimension, like the codimension is not 2, so then you cannot lift to the universal cover and etc. So essentially, like, okay, I present the proof in codimension 1 because it makes sense, but essentially what we are gonna do in codimension 2 or higher is exactly the same thing. So we look for a ball and we try to find also a direction where we can rotate our ball in the Grassmannian so that we cover a wide region and prove that so then we add this in the hypothesis. So if the Gauss map omits such a region, then we are in a totally geodesic hypersurface, or actually submanifold of now codimension bigger than 1. Okay, and so I am a bit over time, so I just finish with a thank you for your attention, and sorry for the problem with the 2 equipments here.
Thank you very much.